And good morning to those of you in the auditorium and also to any of you who are watching from the comfort of your cabin. So I'll just start off with a brief introduction. My name is Ben Church. I am a geologist, and that means that I combine all of the sciences to lead to an understanding of the way the Earth works, really. In a previous life, I worked on oil rigs for a few years all over the world, and I then became a teacher, and I was a teacher for 26 years, where I had a passion for teaching geology and I tolerated teaching geography. And I talked about both in the comprehensive system and also in the independent sector as well. But don't worry, this isn't a lesson. It's my job, I feel, to educate and also to entertain, so no test at the end. As well as the teaching career, I've also led a lot of adventure travel expeditions with young people, and I continue to do that now. And I also lead cultural and educational tours with American high school kids, which is an interesting exercise. And I also collect and sell Cornish minerals. So let's get started. My starting point is the continental jigsaw. So the fact that some continents very much look as though they fit together. So why is this? Well, in 1596, this guy, a map maker, Abraham Ortelius, that's the first recorded, written down observation of these countries, these continents look like they fit together a little bit. And then in 1620, Francis Bacon, he saw that as well. But 1858, the first person to actually produce a map, a fairly detailed map, showing this jigsaw fit was this guy, which is Antonio Snider Pellegrini. So that's the first detailed map, and that's our starting point, really. He did also make some observations that there were some fossils of plants that were found in Africa and in South America, and they looked quite similar. Now, introducing this guy, one of my heroes. He was a German adventurer called Alfred Wegener. And as well as going on lots of expeditions in Greenland, he was actually a meteorologist, and he was one of the first people to use kites and balloons to study the polar atmosphere. And he and his brother, they were both balloonists, and they actually set the world endurance record in 1906 of 52 hours up in a hot air balloon. However, he is best remembered for his development of a theory which we call Continental Drift. So he proposed this theory in 1912 when he was 32, I think, and it was a very simple idea. He said, there's a jigsaw fit. He suggested all of these continents were once joined together, and since they were joined together, they've moved apart. The numbers on the side there, when it says MYA, for future reference, that's millions of years ago. Okay? So he called his theory Continental Drift. Big idea, but it was very unpopular because it challenged all of the long-established views of scientists that everything stayed the same. So the geometric fit actually works best not with the coastline. It works best with the 1,000-meter water depth contour, because that is the true edge of the continent. It's the edge of the continental shelf. There are some little gaps and little overlaps, and those are due to events that happened after the continents broke up. So you might get some erosion of the coastline, or you might get a lot of deposition at the coast as well. And you also get some changes in where the coastline is due to the global changes in sea level. It's nothing new. The global sea level does change. And also, sometimes you get a local change in the land level as well. So, I mentioned the fossils. So, the second line of evidence, you've got geometric fit, number one. Number two is we've got the fossil evidence. So, there were a variety of different types of fossils that were found on continents that appeared to, if they were put back together again, would have been adjacent. So we've got the plant fossils. I mentioned this Glossopteris, a fern, so dinosaur food if you like, but also some of these reptiles. So we've got land reptiles like Synagnathus on the left there, and the Lystrosaurus at the top right. Looks a little bit like a hippo. And then down at the bottom, Mesosaurus. Now, you might think, oh, well, that's a swimmer, but it's a freshwater reptile. No way could that have swum across the Atlantic. The next line of evidence is glacial deposits. So our third line of evidence is that a lot of the continents in the south have a record of glacial deposits, rocks deposited by ice. And these date between about 250, 380 million years ago. Now, you could say, well, maybe the whole planet was frozen. And there have been times when most of the planet has been frozen, but not at this time, because there's evidence in rocks in other parts of the world of fossils, for example, of corals, so indicating much warmer climate. But if you put the continents together, then you get a much more realistic southern pole for the ice. So all of these lines of evidence then suggest that the continents were once all joined up, and they drifted around, and then between 300 and 200 million years ago, you had what's known as Pangaea. All of the land masses joined together as one. And then during the period when the dinosaurs were around, the 165 million reign of the dinosaurs, more of which in a later talk, the Pangaea broke up, first of all into a northern continent, top right there, Laurasia, and a southern continent of Gondwanaland, and since then they've continued to drift apart. So, 1930, our man Wegener died on an expedition in Greenland, and during his lifetime, most scientists did not accept his theory. They said his evidence was weak, but most importantly, they said, where's your mechanism? How does it happen? And he couldn't explain that. They may also have been slightly against him in that his theory, you might remember, was pronounced in 1912, just before World War I, and he was German. So they also said, you're not a real geologist, you're a meteorologist. So, I mentioned the war. Now, wars are horrible things, but they are quite good for science. So in the Second World War, sonar was developed. And the idea of sonar was that you could detect submarines. You'd have a pulse of a sound wave which would travel through water, reflect off the target, reflect off the ship. And because you know the speed that sound travels in water and the time it takes for that sound wave to travel down to the target and back, you could calculate the distance or the depth to the submarine. And then in the 1950s, they used this technique to map the ocean floors. Now, at the time, everyone kind of assumed that the ocean floors were flat. And they're referred to as the abyssal plain, which suggests it's completely flat. But what they discovered was, it's not flat. It's not flat at all. Down the middle of the oceans, you have enormous mountain chains. Now, the diagram at the top, please note, it's got a different vertical scale and horizontal scale. So, if you had it with them both the same, you'd barely be able to see the ridge in the middle. So we've had to exaggerate that. And the reason for that is that these features are so big. Thousands of kilometers long, and this mountain chain is between 1 and 3 kilometers high. So a very, very big feature. But as well as these big mountain chains down the middle of the oceans, they also found some incredibly deep ocean trenches, like the Marianas Trench, which is nearly 11,000 meters deep. So, big features. If we fast forward to 1962, this American geologist, Harry Hess, he suggested that the ocean floor rocks were not as old as everybody had assumed. He proposed that new ocean floor was being created at those mid-oceanic ridges, along those big mountain chains down the middle of the oceans. And he said that, well, the magma comes up there, and then it moves apart, and the new rock moves away from the middle of the ocean. And that then, at the edges of the ocean, where the big trenches are, that's where that material, the oceanic crust, goes down underneath the continents and gets destroyed. Well, the whole idea was that the ocean was spreading. So this theory, remember we had Continental Drift from Wegener, this theory, the second big chapter in the story, is the theory of sea floor spreading. So this was his idea, but again, he couldn't really come up with very strong evidence for it, apart from just the shape of the ocean floors. Now, another World War II development was MAD, a magnetic anomaly detection. So they were using airborne magnetometers to detect the magnetism of submarines, which are metal. They have a lot of iron in them. Now, the Earth does actually have a magnetic field. That magnetic field is generated in the liquid outer core, the red in the middle of the diagram there. And it's generated by movements within that liquid outer core. Now, when magma cools and crystallizes to make rock, the iron-rich particles line up with the Earth's magnetic field at the time. And this paleomagnetism, fossil magnetism, is then recorded in the rocks. Now, the Earth's magnetic field is a bit like a giant bar magnet. It's dynamic. Remember, it's created in the liquid outer core, so it's changing. And the strength of the magnetic field waxes and wanes. And every few 100,000 years, the north and south poles flip. They reverse. The last one was 780,000 years ago. Now, these reversals of the Earth's magnetic field are recorded in the rocks, these iron-rich rocks of the oceanic crust, a dark, dense, black rock called basalt. So you've got the seafloor spreading, we think, happening there, and as the magma, the new crust, cools and solidifies to form the basalt, we're recording that paleomagnetic data. So this produced a striped anomaly, a pattern of normal, the kind of polarity that we have at the moment, and reversed polarity. And what's interesting about this pattern, if you look at the diagrams, they're completely symmetrical. A symmetrical pattern of normal and reversed magnetic anomalies either side of the mid-oceanic ridge. Now, I have been a keen geologist all my life, and I seem to spend all of my life either digging holes or in them. So that's me collecting fossils in Clitheroe in Lancashire many, many years ago. And below me there is my Scouts Geologist badge. Now, my Scouts Geologist badge was given to me by the chap on the left-hand side of that photo. And those two guys, very important geologists. So the guy that gave me my Scouts Geologist badge is Fred Vine. And on the right is the guy with a wonderful name, Drummond Matthews. Now, these two looked at the paleomagnetic anomalies. My diagram showed it as very simple stripes. This is an actual record of paleomagnetic data. But you can still see, especially if you squint at it, the eye of faith, that you've got a parallel pattern of symmetrical anomalies. So in 1963, year before I was born, and the year after Harry Hess had proposed his idea of seafloor spreading, Vine and Matthews, these two British geologists, they published their work about the magnetic features that had been mapped on the ocean floors. And they said, these anomaly patterns are the clincher. They are the conclusive evidence that Harry Hess's hypothesis of seafloor spreading is true. It does actually happen. So they suggested that the only way that you could get this symmetrical pattern would be if you have the new rocks being formed at the center in the mid-oceanic ridges, and then that rock, as it cools, crystallizes, solidifies to make your basalt, that is then moving away from the mid-oceanic ridge. So finally, we start to get acceptance of Wegener's original idea of continental drift. Now, if that seafloor spreading theory is correct, what do you I mean, if we look at the mid-oceanic ridges, they're in red. So what do you think would happen to the age of the ocean floor either side of the mid-oceanic ridge? So as you go further away from the mid-oceanic ridge, what would happen, do you think, to the age of the rocks? Further, if the new stuff is being formed at the ridge, that's the youngest. So as you move away, it gets older. And that has been confirmed. We can date rocks and get the ages of those rocks either side of the mid-oceanic ridges. Now, there's lots of different ways of dating rocks. You can use what's called relative dating, which is just putting things in order, events in order. So there's a principle of superposition, which is basically that the oldest rocks will be at the bottom of a sequence and the youngest rocks will be at the top. Notice I said it's a principle, not a law, because sometimes folding can actually overturn rocks. So we can use the law of superposition, and then we can say, yes, relatively speaking, the further away you go from the mid-oceanic ridge, the older the rocks get. We can also look at the succession of fossils. So we can say, well, if you've got a particular type of fossil in there, which later became extinct, and then a new type of fossil arrives, then those ones with a new fossil must be younger. But we can also use a technique known as radiometric dating. Now, radiometric dating relies on the constant rate of radioactive decay of certain elements, radioactive isotopes. Now, the rate at which these decay is it's a constant rate. And if you know how long it takes for half of what we call the parent, the original element, to decay to the daughter, the new element, the new isotope, we call that the half-life. And if we know what the half-life is, we can calculate the age. So if you're looking at, let's say, uranium to lead decay, the half-life of that is 1 billion years. So if you've got 25% of the daughter, that must mean, right, we've got 2 half-lives. And so it's going to be 2 billion years old. If we've got 12.5%, then it's 3 half-lives, so it's going to be 3 billion years. So this principle of looking at the proportion of the original parent element and the daughter element, that proportion gives us the clue and allows us to calculate the age. So many of you will be familiar with the idea of carbon-14 dating. Now, carbon-14 dating is a really useful technique, don't get me wrong, but the half-life of carbon-14 is only just over 5,000, about 5,200 years. So that means that it's only really useful for archaeological dating, up to perhaps 50,000 years, let's say. Because after that, the proportion of the parent that's left is going to be so tiny that it's going to be very difficult to measure it accurately. So for dating the rocks of the ocean floor, we use a technique called potassium-argon dating. And there we've got a half-life of about 1,200 million years. And that's really good for dating those rocks of the ocean floor. So if you measure the distance of a place where you've got a sample from the mid-oceanic ridge, and you know the age of those rocks, you know how long it took to get there, you can actually calculate the rate at which, the speed at which, if you like, these tectonic plates moved over the surface of the Earth. Now, the rate of growth does vary. So the Atlantic Ocean, the seafloor spreading down the middle of the Atlantic, is about 3 centimetres a year. So you're moving away from America by about 3 centimetres a year. That's about the same rate that your fingernails grow. However, in the Pacific, some of the plate movement there is between 10 and even as high as 15 centimetres a year. So quite a lot faster than your fingernails are growing. And I'll explain a little bit about why that is the case later. So the oldest rocks of all are found on the continents. So if you go up to northeast Canada, you've got rocks that are 4.3 billion years old, dated, as I mentioned earlier, with the uranium-lead dating method. But if you look at this map and you look at the key, what's the oldest ocean floor? Well, the oldest ocean floor, there's nothing older than 208 million years. Very interesting. That's significant. Come back to that later. So we've got seafloor spreading and continental drift being accepted. 1963, this Canadian geologist, John Tuzo Wilson, he combined his work, he'd been looking at volcanic hotspots, places like Hawaii. He combined his work on hotspots with the work of Wegener, continental drift, Hess, seafloor spreading, and Weiden-Matthews, the paleomagnetic data. And he came up with this idea that the whole surface of the Earth is made up of a series of tectonic plates, the theory of plate tectonics. And this really is the unifying theory. It ties together almost every aspect you can think of geology. And it is to geologists the same as, or earth scientists, it's the same as evolution is to biologists. So the idea is, and I do stress with this diagram, it is not to scale, very important. A lot of textbooks get this wrong. That the oceanic and continental crust is, compared to the size of the whole Earth, very thin. Imagine a coat of paint on a football. That's about to scale. So you've got the continents and the continental shelf areas that I mentioned. They're relatively thick. The average thickness is about 33 kilometers. The density of it is relatively low, and most of the rocks there are granitic rocks, so many of you will be familiar with granite. But the crust that we find in the ocean areas, that's relatively thin, perhaps 7 kilometers thick. It's dark and dense, remember the rock basalt, and it's considerably denser than the granite. And the fact that the oceanic crust is denser than the continental crust is very important. Now, the tectonic plates, one plate can consist of both continental and oceanic crust, because underneath the crust you have the very, very top part of what's called the mantle. And that very top part of the mantle is solid, it's rigid. Okay? So the tectonic plates are roughly about 100 kilometers thick. Now, we talked about continental drift. They're moving about over the surface of the Earth. So how can that happen? Well, below the lithospheric plate, the tectonic plate, you've got this layer called the asthenosphere. Now, the top of it is defined by the 1,300 degrees centigrade isotherm. Now, that tells you how hot it is. And that's the temperature at which you're going to get some slight melting. So within that asthenosphere, you've got a zone. It's a very, very small percentage of it is melted. Probably less than 2%, possibly even less than 1%. But the fact that it's got that tiny bit of melt in it allows the lithospheric plates to move around over the surface of the Earth. Below that zone, so below just over 200 kilometers depth, the mantle is solid. And that's something that a lot of textbooks get wrong. So next time you're looking at a diagram of the structure of the Earth and you're reading the accompanying text, check. The mantle is solid, not liquid. Now, if we look at a map of the Earth, we find that geological activity, the things that excite me, like earthquakes and volcanoes, has a very distinct distribution, a very linear distribution. And those lines define the plate boundaries. And if we look at the surface of the Earth, we'll find that about 95% of the surface of the Earth is made up of just 7 major tectonic plates. But there are lots of smaller ones fitting in between them. So if we look at this map here, you can see, for example, straight in the middle there, the African plate, you've got the continent of Africa, continental crust, surrounded by oceanic crust. So a lithospheric plate can be made of both continental and oceanic crust. So let's have a look at how it all works then. So we've got different types of plate boundaries. Now, remember the guy who actually came up with plate tectonics was this guy, J. Tuzo Wilson. His research was into hotspots, and they're unusual because they happen away from the plate boundaries. So that would be somewhere like Hawaii, for example. But we're focusing today on the plate boundaries. So first of all, the one that we've been talking about a lot is the constructive plate boundary, the mid-oceanic ridge where new oceanic crust is being created. Now, along those boundaries, they tend to be offset, and you may see on the diagram there, I've got another slide later which shows it better, that those ridges are offset, they're staggered, and those boundaries that stagger the mid-oceanic ridges are called conservative plate boundaries, because along them you don't have anything created or destroyed. And that's another area of study from J. Tuzo Wilson about transform faults. More detail later. The third type is the destructive boundaries. Now, when we get destruction, we're talking about oceanic crust going down below either more oceanic crust or below a continent. This process is known as subduction. So we can have subduction of oceanic crust underneath oceanic crust, as shown on the left-hand side of the slide there, which forms an island arc, a curved line of volcanoes. We can have oceanic continental, as on the right-hand side of the diagram, where we have a line of volcanoes along the edge of a continent, forming a mountain chain, a cordillera, like the Andes, for example. Now, remember we talked about the age of the oceanic crust, and there was nothing older than 208 million years. Now we know why. Anything older than 208 million years has been subducted. It's been destroyed. Fourth type of boundary is where two continents collide. Now, if you remember, the continental crust is of relatively low density, and that means that it can't be subducted. So it tends to push up and to push down, and that forms big mountain chains, orogenic belts we call them, for example, the Himalayas. So let's have a look at some of these in a little bit more detail. So first of all, the constructive plate boundaries. What happens is that you have a rising plume of magma from great depth, and this will cause doming. And the doming leads to the formation, as you can see in the top right there, of a three-armed rift, and that splits the continent. So a good example of this would be the East African Rift Valley in Africa there. So that's a continent rifting. Now, if that process continues, then in those rifts you will start to get volcanic activity, and you will start to get the formation of basalts, new oceanic crust. So that's a very young ocean. So a good example of that would be the Red Sea. So what happens is that two of the arms continue to rift, and then one of them fails. So we get the opening of an ocean. We've got everything's under tension, so we get lots of faulting, and that allows the center of that ridge to drop down to form a big rift valley. So along those mid-oceanic ridges, you've got these huge trough-like features along the top of those mid-oceanic ridges. Now, because those plates are moving apart, there's reduced pressure, and that means that the rocks near the top of the mantle, because of the reduced pressure, are able to partially melt, and that's what produces this basaltic magma. It's hot, so it's less dense than the surrounding rock, so it rises. It forms at the mid-oceanic ridge, cools, solidifies, moves away from the mid-oceanic ridge, and then the ocean gets wider. Until we have this, a mature ocean, like the Atlantic Ocean. Now, I did mention earlier these curved lines that offset the mid-oceanic ridge. If you look on the lower slide there, you can see quite a good example. I've highlighted it for you here in white. So that is one of these transform faults. So a transform fault then is where we have the differential rate of spreading causing tension, because the way that oceans open is like a pair of scissors. Yeah? So that means that along the length of the ridge there will be different amounts of spreading, and that sets up tension, and that is accommodated by these transform faults. Good example of a transform fault would be the San Andreas fault. That's actually an example of one of these. The reason that they're slightly curved is because of the shape of the Earth. So, name that tune. Johnny Cash, Ring of Fire. So, the Pacific Ring of Fire. So called because around the borders of the Pacific we have so much volcanic activity. Lots and lots of volcanic activity. The reason for all of that is that around those margins we've got lots of subduction going on. And that's that subduction that leads to the volcanic activity. So we'll look first at the one which is really most relevant to us on this cruise. Here we're looking at the destructive boundary where one bit of oceanic plate goes underneath another one at a subduction zone. We know where these subduction zones are because we can detect the earthquakes that happen due to friction between the subducting plate and the overriding plate. So you see where those yellow symbols are? They're earthquakes denoting that inclined zone of subduction. and that zone is called appropriately for me, a Benioff zone. So the Benioff zone then, that tells us where the angle of subduction. And as that oceanic crust is going deeper and deeper, is getting hotter. And it undergoes, this is very important, partial melting. Not total melting, but partial melting. Now, different minerals will melt at different temperatures. And that means that if you partially melt your oceanic basalt, then you will produce a magma with a different composition. You'll produce a magma which has more silica in it. And as well as the oceanic crust that's being subducted there, you'll have all of the sediment that was sat on top of it, all of the mud and sand, and that is also rich in silica. So we've created a magma of different chemical composition, and because of its different chemistry, it also has different physical properties as well. So we've got the partial melting and then the rising of the newly created magma of a different composition, a composition we call andesitic, and this rises up into the crust. Now, some of it won't make it to the surface, and it will cool and crystallize below the surface to form a big, what we call an igneous intrusion. But a lot of it will make it to the surface, and it will lead to volcanic activity on the sea floor, which will continue to build up until the submarine volcanoes poke up above the sea and form a line of volcanoes in a curved pattern, an island arc. And that, ladies and gentlemen, is how the Caribbean was formed. So the Caribbean then is an example of a volcanic island arc formed by the subduction or destruction of oceanic crust going down to great depth and being partially melted. And the nature of the volcanic activity that you get there is very different to that at the mid-oceanic ridges, and I'll be talking about that tomorrow. The second type of boundary we talked about was where we have the oceanic crust being subducted or destroyed underneath the continental crust. Now remember, the continental crust is less dense, so it cannot be subducted. Now here, yes, we get the same idea of a Benioff zone, and where it says accretionary wedge, that's all of the sediments that were on top of the basaltic oceanic crust getting scuffed up and stuck onto the edge of the continent, and that's one of the ways in which continents grow. But again, we get partial melting of the basalt with all of those wet sediments, and it rises up. But this time, instead of it rising up through basalt, it's rising up through the granitic rocks of the continent. And they will go and undergo a little bit of partial melting as well. And that will lead, again, to a different composition of magma. A magma which is chemically different and also has different physical properties, which mean that the nature of the volcanic activity that you get is very different. So here we would get far more explosive volcanoes. So instead of having the pretty lava fountains that you might have at an island arc, here you're going to get the really thunderous great eruptions like Mount St. Helens. We also have the collision boundary. So here it's continent colliding with continent. The ocean has completely closed and all of the oceanic crust has been subducted and destroyed. Because the continental crust is less dense, it cannot be subducted. But as you push up mountains, you also push down a deep root. And in that deep root, you will get partial melting of granite, which again will produce a different composition of magma. It'll produce a magma which is much richer in silica. And this tends not to make it to the surface. It will normally cool, crystallize, and form these great big igneous intrusions, these big granitic bodies at depth. So at depth, we're talking possibly between maybe 5 and 8 kilometers depth. Okay? So a good example of an orogenic belt where we've got this continental collision. An old one would be the Himalayas, a more recent one, you could look at the Alps. And within these mountain belts, you've got these deep granitic intrusions. But with geological time and lots of weathering and erosion and uplift of the rocks, sometimes these granite plutons can actually become exposed at the surface. So I live in Cornwall. And in Cornwall, we have these granite plutons exposed at the surface, forming Exmoor, Dartmoor, Bodmin Moor, and so on. So the whole of Cornwall underlain by this enormous body of granite, so granitic magmas. So, we've covered a lot of ground. It's a big topic, and as I mentioned, it's the unifying theory, really, for earth scientists. So I want to give you some sort of headlines, the points to remember if you want to have a discussion over dinner about this. So the first point is, our first idea is continental drift, that we've got these lithospheric plates, the plates about 100 kilometers thick, moving about on a layer underneath it called the asthenosphere, which is just a tiny, tiny little bit molten, but underneath that we've got the solid mantle. So number one is we've got continental drift. The second point is that the oceans is oceanic crust, which is thin and dense. The third point is continental crust is thick and less dense. Then we've got the idea that along the mid-oceanic ridges, at those big mountain chains, thousands of kilometers long, 2 or 3 kilometers high, there we've got seafloor spreading, constructive boundaries, new material. And then our fifth point, that the oceanic crust is destroyed at subduction zones, where the big trenches are. That's where we get most of our volcanoes and earthquakes, for example, the Pacific Ring of Fire. And it's that subduction which is pulling the rest of the oceanic plate behind it that we think is the explanation of why the Pacific plate moves quicker than in the Atlantic. And then finally, that continents cannot be subducted, so they collide to form great big mountain chains and deep granitic intrusions. So there we tend not to get volcanoes, we get earthquakes. Now, that links neatly to my second talk, which should be tomorrow at 2, The Wonderful World of Volcanoes. I mentioned several times about how different plate tectonic settings lead to the generation, largely through partial melting, of magmas of different chemical composition with different physical characteristics, leading to different styles of volcanic eruption. And I'll be talking about this at length tomorrow in The Wonderful World of Volcanoes. However, things are subject to change, so please do check the Daily Times. So if anybody has any questions, they always need to clear the stage after doing one of these talks. So I will always be over on the left-hand side at the rear of the auditorium if you need to ask me any questions there. Or if you think of a question later, as many of us do, it's that thing of, oh, I wish I'd asked that question 5 minutes later, or 5 hours, or 5 days. Don't hesitate. If you see me around the ship, I love to chat about geology. Nothing I like better than talking about rocks. So please do come and have a chat about that. Later in the cruise, as well as the volcanoes talk, I'll be talking about the geology of Barbados, which is the odd man out of the Caribbean. It's sort of stuck out on a limb. I will also be taking you on a journey to the centre of the Earth, looking in more detail at that Earth structure model that I showed you early on in this talk, and how we actually got that information about the structure of the Earth. I mentioned dinosaurs very briefly. I'll be doing a talk about how the rise and fall of the dinosaurs, but specifically the demise. But also with a different hat on, as well as my geology talks, I'll be doing some talks about adventure travel. So adventure travel all over the world, in Africa, South America, Southeast Asia. The premise there being that when the going gets tough, it makes a good bar story. People want to hear about when things go wrong, not when everything went according to plan. With the expedition work, I will do a talk about that as well. So quite a variety, a mixed bag. So I think a little bit of education, and I hope a lot of entertainment and a little bit of humour as well. So thank you very much for coming, and thank you to the tech team. I hope to see many of you tomorrow. Thank you.